Okay. University has closed campus for the afternoon, so I'm not going to have our class meet in the usual way. What I'm doing is pre-recording this material so that you can watch it anytime between uh, now and Monday or whatever. Since I didn't want you trying to show up to class during a time when the campus is closed. So I hope that everyone stays safe in spite of the weather that's coming our way. So what I'm going to do now is cover section 3.3, which is some applications of determinants, including Kramer's rule and certain geometric applications. So I have just a few problems to go over. All right. So first, what is Kramer's rule? Kramer's rule is a formula for the components of a solution X to a system of linear equations, AX equals B, where A is any square invertible matrix. So we can express each component of solution X using this formula of a determinant of AJ over determinant of A. Now, what is AJ? AJ is a matrix you get by replacing column J of A with B. So now you can compute n plus 1 total determinants of each of these AJs from J equals 1 to n. Let me note that explicitly here. Okay. And then a determinant of A in the denominator, which must be non-zero by assumption because A is invertible. Now, this is not really a practical way to compute solutions of systems of linear equations, because if you do the usual process of row operations on A to reduce to echelon form and then back substitution, for an n by n matrix, that would take on the order of n cubed operations in a general case, maybe less if a lot of entries of A are 0. But a determinant by itself takes order n cubed operations using a similar process because you're working with echelon form. So, but you have to compute n plus 1 total determinants. So the total amount of work here is order n to the 4th operations proceeding in the most efficient way possible. So in other words, even worse if you use cofactor expansions. Now, of course, it would be less if it would be less if a lot of entries of A are 0, but that would help with row operations too. So this Cramer's rule is most useful for small systems of linear equations, like 3x3, 4x4 at the most, where you really want to have explicit formulas for the entries of X. Like maybe the entries of A and B are not numbers, maybe they're expressions involving variables, and so that way you can express a solution X in terms of those same variables. So it does have a use, but not for general purpose solving of systems. Here's a quick proof of Kramer's rule that if I take a matrix A and scale the jth column by xj, then that will scale the determinant also. So the determinant of this modified matrix is determinant of A times xj. Then what I do is I perform a column operation similar to a row operation, where I add to this jth column the other columns of A multiplied by their corresponding x's. This kind of column operation will not change the determinant. Let's see, I have a typo there. Determinant. Okay. So now what does column J equal to? It was scaled by xj before. Then I added in the other columns times their respective x's. This doesn't change the determinant. This scales it. But what is that? That's all the columns of A times their respective x's. So then that's a linear combination of the columns of A where the coefficients in the linear combination are the elements of X. That's the matrix vector product A times X, which is equal to B because X is a solution to AX equals B. So what I've done is, for these column operations, I've replaced column J of A with B. And I know how that affects the determinant. The determinant is equal to the determinant of the original matrix times xj. And the matrix that I have through these operations is AJ. So now I have this relationship. And now I could just rearrange and solve for xj. So that's how Cramer's rule is obtained. It's based on how column operations, similar to row operations, affect the determinant of a matrix. And it helps here that these kind of column operations don't affect the determinant at all. That's really the key step right there. Otherwise, we wouldn't have such a simple formula for each xj. All right, so that's Cramer's rule, but I'll show how it's used in the problems. Here's some geometric applications that we'll also see used. If A is a 2 by 2 matrix, the columns come from adjacent sides of a parallelogram. So in other words, two sides of a parallelogram that are vectors and have a common initial point. Then the absolute value of the determinant is the area of a parallelogram. We've actually seen this before. Now you can think of a triangle as half a parallelogram. So if A is the same kind of matrix, where the columns are vectors that define sides of a triangle that have a common initial point, then 1/2 the absolute value of a determinant is the area of a triangle. You can think of this as a generalization of a familiar area of a triangle being equal to 1/2 of a base times height. In fact, this formula can be derived that way. And finally, we have a 3 by 3 matrix, and the columns are vectors that share a common vertex of a parallelepiped. So you can think of it as a 3D version of a parallelogram. Like one of my students once referred to a parallelepiped as a, quote, parallel box. Then the absolute value of the determinant of this 3 by 3 matrix is the volume of the parallelepiped. All right. So they can't be just any three sides. They have to be three sides that share a common vertex. That's important here. Okay, now I'll get into the problems. First, a couple of Cramer's rule. Here we have a system of equations, two equations, two unknowns. So in matrix vector form, it's this matrix A, the coefficients of the x's, times x is equal to B, this right-hand side vector of right-hand side values. So now I take this matrix and replace each column in turn with B. So here I replace the first column with B, and that's A1. Then I replace the second column of A with B, and that's A2. So now I take the determinants of A, A1, and A2, using the familiar formula for determinant of a 2 by 2 matrix. And now that I have all my determinants, I can just apply Cramer's rule. So x1 is determinant of A1 over determinant of A, x2 is determinant of A2 over determinant of A, and now I have my solution to this system, to AX equals B. Now I'll show same thing with a system of three equations and three unknowns. So the system of a 3 by 3 matrix. Notice some unknowns are missing here, and that's why we have some 0 entries. And here are my right-hand side values. So I do the same thing. I replace the first column of A with B. So 403 goes here, get A1. Then I replace the second column of A with B. And then I replace the third column of A with B. And I get A1, A2, A3. Now I need determinant of A and determinants of all three of these matrices. And I'll use a cofactor expansion for each of these. So for A, I'm just going to do a cofactor expansion along the first row. So 1 times the determinant of this 2 by 2 matrix minus 1 times the determinant of this matrix, -2, 5, 0, and -5. But you get by deleting the first row and second column. And then I work all that out from there in terms of these 2 by 2 determinants. For A1, I do a cofactor expansion along the second row because there's only one non-zero entry. And remember, the sign pattern for second row is minus, plus, minus. So for first row, your alternating signs start with a plus. Second row, alternating sign pattern starts with a minus. So I have -5 times the determinant of this matrix, 4, 1, 3, 1. It comes from deleting the second row and third column. So then I work all of that out to get the determinant of A1. For A2, I do a cofactor expansion along the first row. There's no clear-cut choice in this case. So I have 1 times the determinant of this 2 by 2 matrix, -4 times the determinant of this matrix, -2, 5, 0, minus 5. Actually, that's actually the same matrix that appeared here with A. And work out that determinant. And then for A3, cofactor expansion along the second row again. So I have minus a minus 2 times the determinant of this matrix, 1, 4, 1, 3, that you get by deleting the second row and first column. So now I have all my determinants, A, A1, A2, A3. So now I can work out the three components of X. So determinant of A1 over determinant of A, determinant of A2 over determinant of A, and the determinant of A3 over determinant of A gives me X1, X2, X3. All right, next, geometric applications. Find the area of a parallelogram with these vertices that I've plotted here. So here's first one, minus 2, minus 1, 0, 7. 7 minus 3 is down here, and then 9, 5 here. So what I do is I pick any vertex. I'll pick this one, 0, 7. And I need to choose the adjacent vertices. So minus 2, minus 1 down here, and then 9, 5 over here. So not this one. So then I subtract these points to get edges. So I have this vector that's pointing in this direction, so away from this vertex. Minus 2, minus 1, minus 0, 7 gives me this vector that starts here, ends here. Similarly, I have the edge that starts here at the same point and goes over here. So that's 9, 5, minus 0, 7. So from there, I get vectors that define two adjacent sides of a parallelogram. So I have this vector that's minus 2, minus 8, and then this vector is x coordinate 9, y coordinate minus 2. So now I take these vectors that define adjacent sides of a parallelogram, again by subtracting a common vertex, and I put them in a matrix. So minus 2, minus 8 is the first column, 9 minus 2 is the second column. Then all I got to do is take the determinant of this matrix and take the absolute value, and that's my area. One thing that's interesting is that taking this problem out, I chose the wrong vertex. So I had this edge, and because I hadn't visualized this yet, I made a mistake and went from this same vertex here to this one, which is not an edge. And I actually still got the correct area, which I thought was interesting. But I have to take some time to prove whether that's something that's true in general. So don't do that. Make sure you choose one vertex to serve as a common vertex of two adjacent edges, and then choose the vertices that are opposite it on the other ends of those edges. So don't choose a pair of vertices that describes a diagonal. So I can't guarantee that will give you the correct area. Another geometric problem, volume of a parallelepiped. So we have one vertex that's conveniently located at the origin, and then we have vertices at these 3 points. So we're given that these define adjacent sides. So all you got to do, since they're at the origin, there's no need to subtract anything in this case. So you can just take these points and make them columns of a matrix. So then you can just take the determinant of this matrix and take absolute value, and then you have the volume of your parallelepiped. So I'm just going to do a cofactor expansion along the first column. So I have 2 times the determinant of this matrix, 5, 3, 4, 0, and then nothing, and then minus 5 times the determinant of this matrix, 1, 6, 5, 3. So this 2 by 2 determinant goes here, and you wind up with a volume of 111. Okay. Now here we have a parallelogram that's described by 2 adjacent sides, these vectors. But then the parallelogram is transformed by multiplying these vectors by this matrix A. So what's the area of the image of parallelogram S under this mapping? So if you just want the area of a parallelogram, you take a determinant of this matrix, but that's not what you want. It's the area of a shape you get by multiplying by A. Now, if you take a parallelogram and multiply it by a matrix such as this A, you get another parallelogram. So, so you want the edges of adjacent sides of that parallelogram. Now, how would that go? If I define a matrix B to be matrix consisting of these vectors B1 and B2 as their columns, and then I apply the transformation x goes to ax to B, then I have a matrix product AB that has these columns. So these vectors are adjacent edges of my new parallelogram. This is the one that I want the area of. But since these are the columns of a matrix product AB, if I want a determinant of this, remember the determinant of a product is a product of the determinants. Is go ahead and take the determinant of a matrix that comes from these vectors, and then, so that's the area of your original parallelogram, then multiply that by the determinant of your transformation matrix A, and that will give you the correct area. So the area of your original parallelogram turns out to be 4, and the determinant of a transformation matrix is 9, so the area of a transformed parallelogram is 36. So this all comes from keeping in mind how you get the vectors that define the new transformed parallelogram. And it just comes from multiplying them by A. And then we take advantage of the fact that the determinant of a product is a product of the determinants. Last problem real quick. Suppose we have a triangle, vertices are the origin, and then V1 and V2. Then because one vertex is the origin, the vectors V1 and V2 describe two sides of the triangle that share this common vertex at the origin. So since V1 and V2 are vectors that describe two of the sides of a triangle, you can just put them in a matrix and then take 1/2 the absolute value of a determinant, and then you have the area of your triangle. All right, so that's it. That's all the problems for this section. So I hope, as I said, I hope everyone stays safe from the storm, and I hope to see you in class on Monday when we start Chapter 5.